Hello, welcome to another problem session. Here's a problem from that goes with this chapter of Physics Bootcamp. It's not in that chapters, but some similar problems are there for you to practice. And okay, so the situation is let's draw it out. So here's a ground, and here is an athlete is trying to jump. The center of mass is at this height at now, okay, time 0 at this time, and he pushes and normal force is up. As the normal force increases, his center of mass goes up, and maybe he just barely left the ground, and his center of mass is over here, and this is half a meter. At this point he has some velocity v0, and after that acceleration is g, and so let's say center of mass, let's call it a dot here, and the dot goes up to here, which is 1.2 meters. At that point v must be 0, because at that point he starts to return. After that, we're supposed to find in this time frame. This is t equals to 0.8 second, and this is t equal to 0. What's the average force? And then supposed to find what's the peak force. That's part B. Okay, so when you look at this situation here, 0.8 second situation, change in momentum will be equal to impulse, right? So change in momentum, so if you look at the y, so this is the y direction. So P at y, and so this is T final and this is T initial. If you look at this situation, TF minus P of y at T equal to TI. That's the change in momentum. This must be equal to during this time, what's the impulse on it? So it will be impulse, net impulse, y component. Okay. So and if you look at just the for this we need to know the forces. So during this time there are two forces on him, right? So during this time there are two forces. There's a weight mg, and there's normal, which depends on the time. And we're supposed to get look at just the average first. Okay, so we'll just look at the average impulse. So this will be some kind of average normal force, minus mg, and that how much time it acted on, be equal to that, right? So from this we can see that this is given, this is given, this is given. This is equal to, at the beginning is 0, it's at rest, So that's 0. So we need to figure out velocity at this, and then we'd be actually get that because the momentum. To figure out, that means I need to figure out v0. So this is m v0, because v0 is upward, y component is v0 itself. So we need to figure this out. Now, if I look at motion, this motion, I can figure out v0. So this is not enough to figure out v0. I need to use this other part to figure out v0, because that's all under gravity. So t greater than 0.8 second to t top. At that point, we can use the v equals to v square equals to v0 square minus 2 gh in the y component. So this is 0. So this is v0 is actually square root of 2 gh. Positive becomes just take a speed, and that's going to be square root of 2 times 10 times h. H is 1.2 meters. So let me calculate that. So I'm going to use this calculator. So two times 10 times 1.2 meters, and that's 4.9 or 5. So let's look at 5. This is 5 meters per second. Okay, so I got that, and m is 80 kilograms. So I can solve for Fn bar, the average Fn bar. This bar means average here. So m, I have a mv0 over delta t plus mg, and so you can see here normal force, average normal, is more than the weight. Otherwise, how is going to rise, you know? So m is 80 kilogram, and this is 5, and delta t is 0.8 plus 80 times 10, and so this is 100, so 1300 Newton. Okay, so this is A. To get B, you can see that the average is somewhere here, right? So this area under this is what the actual impulse is. Actual impulse, we use this over here, but actual impulse is, if I look, this is the Fn max. So the area under this is a, you can find the area under over here, half the triangle, that means 2 times half the triangle. It's just going to be Fn max times 0.4 used to be half the triangle times 2, right? There are 2 triangles there, so it's like that. So this is actual impulse, okay, from the normal force. That should equal to the average impulse we have found times delta t, which is 0.8. So the maximum is actually twice the average. 2 times the Fn average, and which is 2600 Newton. So this is the B. So and thing to notice here is that the normal force is actually much greater than mg. So a lot of times students kind of memorize this for some reason. So you can say Fn is actually not mg. And not only that, Fn varies with time here. So to recap, what are the things that we did here is first is a focus on center of mass. And when we analyzed two separate time ranges, this and things beyond that. So in the first time frame, we found this is Newton's second law written in change in momentum in impulse form. I need to make sure that the impulse was net impulse, and once we got through this, we were able to identify what we needed to find from the second time frame. So we need to find V0 from, and there we used constant acceleration, because at that point in time, in this time frame, only gravity is acting. So those were the critical things. And for part B, we applied the actual area under the curve for force Fn t versus t graph. And if you do the gravity, for the gravity, you will see that the mg part is all like that. Even beyond 0.8, gravity is still acting, but this guy's stopped acting. Mg is still acting. So the impulse here is just average impulse, is same as the maximum impulse for gravity, because gravity is not changing. Okay, I think this is a good problem. You should try to do this yourself and find similar problems like that. We'll see you in the next video.